write out all the notes that we need. So let me share the screen. So can you confirm if you are able to see my screen?
Yes.
Okay, there's so the topic we're going to work on today is this one for maps. Let's see. So we did the complexes yesterday. I think we stopped here, somewhere here. I think someone is trying to join. Let me admit them, then continue. So we'll start here from maps. So here is just a definition. A map on a compact surface will simply be a pattern in which each vertex has valence, at least 3. That is, the valence of each vertex will be either 3 or more. So again, let's get the perspective on this. We started with the tilings. Tilings was just an arrangement of polygons on a compact surface, satisfying some conditions. Then we looked at a special case of tilings, which we called patterns. Patterns are simply tilings, but they have some extra properties in the sense that I think we don't allow vertices of valence 1, and we don't allow, what else don't we allow? We don't allow faces that are one-sided. So no one-gons, no vertices of valence 1. That's the patterns. So we went a step further and looked at a smaller set of patterns that we called complexes. So complexes, we said we require the sides, the faces to have valence at least 3. I mean, the vertices to have valence at least 3, and the faces to have at least 3 sides. That's the complexes. Now, inside the set of complexes, we considered a special case of the regular complexes. Regular complexes require that all vertices have the same valence, and also requires that all faces have the same number of edges. So that now we are looking at patterns again, another type, smaller subset of patterns, which we call maps. So complexes will qualify as maps as well. The complexes on the compact surfaces, they definitely qualify as maps. So I'll repeat the definition again. The definition says the map on the compact surface is simply a pattern in which each vertex has valence at least 3. So you cannot have a vertex that has valence less than 3. So no vertices of valence 1 and no vertices of valence 2. Now for a positive integer n, a map on a compact surface is n colorable if given the n colors, each face of the map can be colored with one of the colors so that no two distinct faces sharing an edge have the same colors. So we don't have to use all the n colors for this definition to work. Yeah. So any number of colors that are enough to color will work. Even if they're more than enough, we still say it's n colorable. So here are some two examples of maps. These are maps on the sphere. So the first map, there's a vertex that is not visible. I just copied this diagram from the book, but it's not very clear. There should be another vertex on that end. See, there is this edge coming from this vertex, so it drops down all the way onto the edge that you can't see clearly here. So this is a map on the sphere, and it has how many faces? There's one face on top here, because the sphere will also include this top part. So there's one face here which has two sides. It's two-sided face. There's a second face on this side which has how many sides? 4. There's a third face on this side which has four edges. And also there's another face at the bottom which has only 2 edges. Is that making sense?
Yes.
So
Yes.
So the other thing that we have is this is another map as well. It's actually the same map, but now it's drawn on the plane model of a sphere. The same map. This same map is drawn on the plane model of the sphere. So this top one is this is the top face. That's the bottom face, and these are the 2 sides. So this is the map on the sphere itself, but this is just if you draw it out on the plane model of a sphere, then we are okay. There's a dog here that is noisy. Let me see if I can get it out of the house. Okay, I'll be back in 1 minute. So we have talked about coloring a map on a surface. So we talked of coloring a map previously. Here we talked of coloring a map. So we want n colors, and we want to color the map in such a way that no 2 faces, distinct faces that share an edge have the same color. So let's see how many colors we need to color this map on the sphere. So if you are to color this map on the sphere, how many colors would you need?
3.
There are 3, okay. So if you color the top with one color, you can't use the same color for these 2 sides because they share an edge with that top face. So you need 2 new colors for these faces on the side. But the color that you used at the top can be repeated again at the bottom because the bottom face and the top face don't share an edge. So 3 colors are enough. Okay. So based on the statements you have made earlier, we can make the following remark that if you have 2 integers, n1 less than n2, if a map is n1 colorable, then it is also n2 colorable. That is, if n1 colors are enough to color, it means any number of colors bigger than n1 will also be enough. The reason for this is we saw earlier that when you're given the colors, you don't have to use all of them. The second thing says that if a map has F faces, then it is definitely F colorable because F colors will be enough to color each of the faces. You may not need all the F colors, but F colors are definitely enough because you can, what it means is that you can color each face with a different color under those conditions. So that still qualifies as a coloring. Now we try to look at some results, things that we can use on maps. So we know this. We know very well that the Euler characteristic is given by this equation, this expression, V minus E plus F. Why is this true? This is not making sense. Just hold on. We have 2E equal to 3V3 plus 4V4. So there's you can obtain this as follows. There's this V can be written as or rather twice the number of edges can be written as 3V3 plus, so this can be 3V3 plus 4V4 plus 5V4 and so on. I don't know if you get that. That is from the previous equations you set up yesterday. This 2E can be written as 2E is equal to 3V3 plus 4V4 plus 5V4 and so on. So, but if I replace each of the larger numbers so that I have, instead of having 3V3 and 4V4 and 5V5, I have 3V3, 3V4, 3V5. So I will have reduced the term, the expression on the right-hand side, so that now it will no longer be an equality. It will be 2E will be less than or equal to 3. And then in brackets, you have V1, V3 plus V4 plus V5 and so on. So that twice the number of edges will be greater than or equal to 3 times V. So that 2E over 3 will be bigger than V, right? So if I replace V with 2E over 3, I end up with an expression which is bigger on the right-hand side. I don't know if I'm making sense.
Yes.
Okay, at least one person has said yes. Can we get 2 more people to second? So what is important is you need to see that this quantity, 2E over 3, is bigger than V. So that's what I was trying to explain. This quantity, 2E over 3, is bigger than V. So if we replace V by something bigger, then what I have on the right-hand side will be bigger than what is on the left-hand side. That's why this changes to an inequality instead of the equal sign. So once you set that up, you can simplify this expression to F minus E over 3. So when you can simplify this and rewrite it and make E the subject, and when you do that, you end up with this inequality that E is less than or equal to 3 multiplied by F minus chi of X. So if you multiply both sides by 2 over F, we obtain 2E over F is less than or equal to 6, 1 minus chi X over F. So let's see what this quantity actually represents. This quantity seems to represent the average number of edges of the map counted per face. So this gives you the average number of edges per face. So that some faces may have this number of edges, or fewer or more. But this will give you the average number of edges per face. So we are going to say a little more. Now, suppose n is a positive integer, and this quantity. So this is the average number of edges per face, or at least something bigger than that. Let's go back so that we see this. So this quantity is bigger than the average number of edges per face, right? So if you consider a value of n that is more than the average number of edges per face for all maps on X, then all maps on X are n colorable. Now this is I have not done the proof for this, so now you just have to take this as the gospel truth. So if this equation is true, suppose this is less than n for all maps on a compact surface X, which has more than n faces, then all maps on X will be n colorable. So this tries to tell you the number of colors you need to color any map on this compact surface, as long as the map has more than n faces. Okay. So we try to set this up for the sphere and the projective plane. For the sphere and the projective plane, we know that the Euler characteristic is positive. So if this will be a fraction here, the smallest value of n that will satisfy this inequality will be 6. Because the quantity in here will be less than 1, you'll have to take off a fraction from 1. So a fraction multiplied by a 6 will be strictly less than 6. That is because the Euler characteristic for S and P are both positive. So it means 6 colors are enough to color any map on the sphere or the projective plane. So we don't know if this is the smallest number you need, but at least it gives us an upper bound on the number of colors needed to color any map on the sphere or the projective plane. So we know that if you have any map, this tells you that if you have any map on the sphere of the projective or the projective plane, 6 colors will be enough to color it. We can test this for the torus and the Klein bottle as well. We know the Euler characteristic is 0. So this number here is 0. And that means the smallest value of n that will work for this inequality is 7. So that means any map on the torus or the Klein bottle will be 7 colorable. 7 colors are enough to color any map on the torus and the Klein bottle. Are we together? So this is all based on this statement at the top. There is a whole proof of this statement in the textbook, but I have not included in the slides. So this statement at the top here is what allows us to come up with these upper bounds for the number of colors required to color any map on these compact surfaces. You can hear me?
Yes.
Okay. Good. So what I'm writing here is just a summary of the results that we have worked out. So any map on the sphere or the projective plane can be colored with 6 or fewer colors. Later on, we shall see that you can color on the sphere. You can find a better lower bound, a better upper bound. So 6 is not the least upper bound for the sphere. And any map on the torus or the Klein bottle can be colored with 7 or fewer colors. So the chromatic number of a map is said to be the smallest integer n, such that the map is n colorable. So any single map on a compact surface will have its own chromatic number. Okay. So, but the results we've obtained before give us an upper bound for these chromatic numbers. So, for example, for the sphere or the projective plane, there's an upper bound of 6 for the chromatic numbers of maps on these compact surfaces. So what it means is that any map on the sphere or the projective plane has a chromatic number which is either 6 or less, right? The same for the torus or the Klein bottle. Any map on the torus or the Klein bottle has a chromatic number which is either 7 or less. So we'll make one more definition. So the coloring number of a compact surface X is supposed to be the minimum number of colors required to color all maps on a compact surface. So you can obtain this by simply looking for the maximum of the chromatic numbers of the maps on X. Now, this gives us an upper bound, but it may not give us the coloring number. So if we want to confirm that 6 is a coloring number for S of P, we need to be able to find a map on S of P which cannot be colored with fewer than 6 colors. If you can find such a map, then we are guaranteed that 6 will be the coloring number of the sphere or the projective plane. So the same for the torus or the Klein bottle. If we can find a map on the torus of the Klein bottle that cannot be colored with 7 or fewer colors, with fewer than 7 colors, then we can conclude that 7 is actually the coloring number for the torus or the Klein bottle. Some of these concepts were also in SMA 250, so they should not be entirely strange. So here we look at, these are covered in detail in the textbook. So you could go back to the textbook just to confirm this, that a regular complex of type 5-3 with 6 faces requires 6 colors. So that means 6 should be the coloring number for the projective plane, because we found a map on the projective plane which cannot be colored with fewer than 6 colors. And on the torus, we can also find a map. The map in particular we are talking about is this regular complex of type 6-3, which has 7 faces and requires 7 colors. So you can't color it with fewer than 7 colors. That means that the coloring number for the torus is also 7. So that any map on the torus can be colored with 7 or fewer colors. So now we can do similar things for the Klein bottle and the sphere. And for the sphere, it has been shown that proof is not trivial. The proof for this 4-color theorem, where it shows that the coloring number for the sphere is 4. That means any map on the sphere can be colored with 4 or fewer colors. And you don't need more than 4 colors to color any map on the sphere. And the rest are coloring numbers for the projective plane, for the torus, and the Klein bottle. So for the Klein bottle, you see the number is less than 7. The upper bound was not a coloring number. The upper bound we got earlier, this one of 7. It was close, but it's not quite the coloring number. For the torus, it turns out to be the coloring number, that is 7. But for the Klein bottle, 7 is just an upper bound, but it's not the least upper bound. So it's not really the coloring number. And it can be shown that the coloring number for the Klein bottle is K, which means that any map on the Klein bottle can be colored with 6 or fewer colors. So this top part talking about the complexes on the projective plane, regular complexes on the projective plane and the torus, you can find them in the textbook, the details. They're actually drawn in there. So you've noticed that all these surfaces we have considered, they have non-negative Euler characteristic, because the sphere has Euler characteristic 2, the projective plane has Euler characteristic 1, the torus and the Klein bottle, I think, both have Euler characteristic 0. Is that correct? So we want to consider surfaces whose Euler characteristic is negative. So to do that, we do the following. We set up the Euler characteristic here to be negative. So we have a compact surface of negative Euler characteristic. So suppose we pick n to be a positive integer, and we suppose that a map on X has more than n faces. So you can put that in this form. The smallest value that f can take is n plus 1, because if the number of faces is more than n, then the smallest value that f can take would be n plus 1. So with your knowledge, since both f and n plus 1 are positive numbers, if you get the reciprocals, this inequality is reversed. So we have this inequality. Now we have picked the Euler characteristic to be negative. So if you multiply both sides of the inequality by the Euler characteristic, since it is negative, the inequality is reversed again. Instead of less than or equal to, now you have greater than or equal to. So we have this relation here, inequality. Now you can also multiply both sides by -1. If you multiply both sides by -1, this relationship, the inequality reverses again, so that you have this less than or equal to. Then after multiplying by -1, you can add 1 to both sides. Then you end up with this inequality. So then you multiply both sides by 6, and you have 6, 1 minus chi x over f will be less than or equal to 6, 1 minus chi x over n plus 1. So there's a reason why you multiply by 6, and there's a reason why we will target this expression, 6, 1 minus chi x over f. The reason for that is a theorem we saw earlier. We'll come back to this. Let's just go back to the theorem. There's this theorem that says if this inequality is satisfied for all maps on X with more than n faces, then all maps on X are n colorable. So we just need to find an n which satisfies this equation. And if it does, then all maps on F with more than n faces will be n colorable. Are we together? So that is the motivation for multiplying by 6 and getting this set up. So now, to find a value of n that is bigger than this, it's enough to find a value of n that exceeds this one, right? So if I find a value of n that is bigger than this term on the right-hand side, then it will automatically be bigger than this. So it will satisfy my inequality, that 6, 1 minus chi x over f will be strictly less than n. So I need to find the value of n that is bigger than this. Okay, so let's do that. So we look for these values of n that are bigger than this, and then this will guarantee us that, as we have seen earlier, if we find those values, we'll have found values of n again that are bigger than this term. And then that means that all maps on the compact surface X with more than n faces will be n colorable. So if you set this up, you want values of n which are bigger than this, you can simplify it to this. This is simple algebraic manipulation. I don't think you'll have any trouble with this. So there you are. Then you rewrite this inequality. You'll end up with a quadratic inequality in n, right? So if you apply the quadratic formula, you find that the positive integer values of n must exceed this. This is one of the roots, right? It must exceed this. The other root, I think, will be negative. So if you want the positive ones, you want one that will exceed this. If you are to draw this as a quadratic curve, it will be a curve that is facing upwards. So one root, I think, will be negative. You can confirm that yourself. The reason for that is if you have this as negative minus, the smallest possible value you can get for this quantity in here is it's for the sphere, right? No, but we are looking for negative, right? When the Euler characteristic is negative. So this, what is in the, if the Euler characteristic is negative, what is in the root sign here will always be positive, correct? So this square root will definitely be, the square root of what is in here will be bigger than 5. And 5 minus something that is bigger than it will give us negative. So the one root will be negative. So the only positive root is this one. And we want values of n that will keep this quadratic equation greater than 0. So those values will have to exceed the positive root, since we are looking also for positive values of n. Are we together?
Yes.
Good. So now, since this may be a fraction, for you to find the smallest integer that is larger than this, you will have to add, you will add 1 to it. Right? Then you take the floor function after you add 1. So for instance, if I have a number like 4.3, I could take the ceiling function of that to get the smallest integer that is larger than 4.3. That will work. But I can also do the following. I could add 1 to 4.3. Then I get 5.3, right? Now the flow of 5.3 will be 5, which still gives me the same condition. The same answer that I'm looking for, the smallest integer that is larger than 4.3. So this, if you think along those lines, you'll be able to see that the smallest integer that satisfies this, that is larger than this, will be this, the flow function of this thing in here. So this number here is called the Hewood number. And it gives you the smallest integer that satisfies this inequality. So this gives you an upper bound for the number of colors needed to color any map on this compact surface X, as long as the map has more than n faces. So once you find the Hewood number, you have a number which guarantees that any map with more than n faces can be colored using that Hewood number. So this is just a definition. So recall that we are only looking at compact surfaces that have negative Euler characteristic up to this point. All this last part we are looking at is strictly for compact surfaces with negative Euler characteristic. So it leads us to this theorem. It says that if X is a compact surface with negative Euler characteristic, any map on X will be HX colorable. So that gives HX, the Hewood number, gives us an upper bound for the chromatic numbers of the maps on X. We don't know if it will give us the coloring number, but it's a good start. The coloring number can be smaller, but at least this gives us an upper bound from which you can work. So a strange happening is that the results we have derived for the Hewood number were worked out for compact surfaces with negative Euler characteristic. But we can still apply the Hewood number to these other surfaces which have non-negative Euler characteristic, and we still get upper bounds. So it actually gives you the coloring number for the sphere. I think it gives the coloring number for the projective plane. It does for the torus as well. But for the Klein bottle, we saw the coloring number was 6. So the Hewood number misses it by 1. It gives you 7 instead of 6. But it still gives you an upper bound that is really close. So that is captured in the theorem, this theorem. So, and these are the different possibilities for the Hewitt number for different surfaces. You can try and you know how to compute the Euler characteristics of these surfaces. We gave out the formulas for computing them. So you can go back and try to compute the Euler characteristic using those formulas. Once you have the Euler characteristic, you can compute the Hewitt number. And the Hewitt number will give you an upper bound for the coloring numbers of the surfaces. So the way this is worked out is 3p. We saw earlier that the sum of the, it's possible that the connected sum of the projective plane and the torus is equal to the connected sum of 3 projective planes. We have seen that. Using the circulation rules, we're able to show this. So when I put equal here, what this simply means is that 3p is the same as the connected sum of 3 projective planes, is homeomorphic to this connected sum of a projective plane and the torus. The same applies to the others. 4p is the same as the connected sum of the Klein bottle and the torus. You can try to show that this is the case. Use the circulation rules that we learned. The same applies for 5p. 5p is the same as the connected sum of the projective plane, or rather is homeomorphic. When I say same, what I really mean is homeomorphic. It's homeomorphic to the connected sum of a projective plane and 2t. So the idea is the same throughout. And when you go back to the formulas for computing the Euler characteristic, you can now apply them here in the Hewitt formula. Once you find the Euler characteristic and work out the Hewitt number. I could try to go back and see where the formulas are. Yeah, here they are. This is how you obtain the formulas for the connected sums of the compact surfaces. I think you have, we went through this. So this is how you get the Euler characteristics. Once you get them, you can just plug them into the Hewitt, the formula for the Hewitt number, and you will be in business from that point on. So that brings us to the end of the class for today. Most of this information, again, I say it is in the textbook. So it is important that you go back and read the textbook so that you have a better understanding. I will share the video as well. You are also free to ask questions now before you go.
Yes,
Yes, Achola. Achola, I can't hear you.
I'm requesting if you can help us with
Can
the
anyone
login
hear what
code
Achola is saying? I thought I had given out the enrollment code for SOMAS. Did I give it out earlier?
But the one I was insisted with was that.
Are you the only one who has not been able to access it, or everyone?
The one I accessed was invalid.
So is there anyone else who has a problem accessing SOMAS? Hey, Momanyi, are you able to access SOMAS for SMA?
Yeah, I've been able to access.
So Achola, baby, you have been kicked out of the university.
Not really.
Hey, you're persona non grata. Let me try to get the code right away. I'll put it in the chat.
Okay.
You can ask questions as I do that.